In this video, we're going to explore an important distinction in analytical chemistry, the difference between atomic spectroscopy and molecular spectroscopy. Even though both techniques use the light to study matter, the kinds of information they provide and the principle behind them are very different. Understanding this difference is essential for choosing the right technique for a chemical analysis. Let's start with atomic spectroscopy. In atoms, electrons occupy well-defined orbitals such as s, p, d, and f. These energy levels are extremely sharp because atoms have no chemical bonds, no molecular vibration, and no rotation. That means their transitions are purely electronic. Electrons simply jump between these discrete orbital energies. So atomic spectroscopy examines the most fundamental electronic structure of elements without any of the complexity of molecular bonding. Because these transitions are sharply defined, each atom absorbs and emits light at very specific wavelengths. This is why atomic spectra looks like isolated, like a razor-thin line, almost like the element's barcode. These lines are so precise that even tiny concentration of element can be detected. Now, let's compare that to the molecular spectroscopy. Well, molecules are more complex than atoms because they don't just have electronic energy levels, they also vibrate and rotate. Every chemical bond behaves a bit like a tiny spring, and the entire molecule can rotate in space. These additional motions introduce many more allowed energy transitions. As a result, molecular spectra are typically broader, richer, and more structured than atomic spectra. Techniques like UV-Vis, infrared, Raman spectroscopy, or fluorescence fall all under the molecular spectroscopy. Because these motions depend on the way atoms are connected, molecular spectroscopy tells us about functional groups, bonding, molecular shape, and chemical environment, things that atomic spectroscopy cannot reveal. To understand how atomic spectroscopy works, I brought an example of the atomic absorption spectroscopy instrument. So, to know that it's important, first we need to understand the heart of this instrument, which is called hollow cathode lamp. This lamp produces the very specific wavelengths of light that atoms will absorb. Let's walk through and how it works step by step. We start with a basic setup. Inside the lamp, there are two electrodes, the anode, which is positively charged, and the cathode, which is negatively charged. They are sealed inside a small glass tube that contains a low pressure inert gas, usually argon or neon. In our case, it's argon, let's say. The key details is that the cathode is made from the same element you want to measure, like a sodium, copper, calcium, magnesium, and so on. So let's consider in our case that we are measuring calcium, that our sample contains calcium, and that our cathode is also made from the same calcium element. When we apply a voltage across these electrodes, the inert gas becomes ionized. This is our argon. For example, the argon atom can lose an electron and form positive ions, like here you see in the bottom. So now the inside of the lamp contains fast-moving electrons and positively charged argon ions because of this high voltage. So these charged particles start to accelerate towards the oppositely charged electrons. The argon plus ions will move towards the cathode, while the electrons will move towards the anode. So the next step is very important, and it's called sputtering. Now, the positively charged argon ions that were ionized, they are attracted to the negative cathode, as I just mentioned it. So they strike it with enough energy. These argons, they strike enough energy to physically knock out the atoms from the cathode surface. As you know, we have a calcium on the cathode surface, and it will knock that out. So the knockoff atoms are of the elements we want to analyze. So this process of ejecting atoms from the cathode surface is what we call a sputtering. Now that these metal atoms are in the gas phase, they can collide with energetic electrons and other ions inside the lamp, because those knocked out calcium ions, they're calcium, now they're free now. So now they will be knocked out, they will collide with electrons or other ions. So some of this collision gives atoms enough energy to become, call it, excited, meaning that their electrons jump to higher atomic orbitals. So atoms do not stay for too long for excited state. So it quickly excites and it quickly comes back to the ground state. So when they do that, they release energy. When they relax back down to the ground state from the excited state, they release energy, and they release it in the form of light. And here's the key point. They emit the light at very, very specific wavelengths that are unique to that specific element. In our case, it's calcium. That's why they built this cathode tube source instead of just shining any light. So they need that very, very specific wavelengths, and that's the only setup that they can get the exact same energy, the wavelengths, to excite the calcium ions. So now that we understand how the hollow cathode lamp creates the characteristic of light, let's shift to the sample side and look what happens inside the flame before the light even reaches the detector. So now we have these wavelengths. Now we have a source to excite the sample. So now we have a sample in mostly the liquid sample in some kind of glass. So when your liquid sample is introduced in the flame chamber, so usually through the nebulizer, it first gets converted into, we call it, fine aerosol mist. So this nebulizer is going to evaporate, turns it into aerosol mist. So these tiny droplets are carried into hot flame, where several important processes happens in sequence now. So now what's first? The droplets dry out, which makes sense. We have very, very high temperature. The solvent evaporates, leaving behind a tiny solid particles of the dissolved analyte. As the particle move deeper into the flame, they experience even higher temperature. So this causes them to evaporate, forming a gaseous molecules. But wait, the molecules, we don't want molecules. It's atomic absorption. The atomic absorption doesn't measure molecule, it measures free atoms. So the next step is, of course, the atomization, where the high temperature of the flame breaks chemical bond and separates the molecule into individual atoms. For example, if your sample contains calcium chloride, the flame temperature is high enough to split it into free calcium atoms and free chlorine atoms. So at this point, the goal is to create a stable population now of a neutral ground state. So we split that into two free atoms, the calcium and chlorine atoms. The next step, they're in the excited state. So now the next step is, of course, to take them to the ground state, because only ground state atoms can absorb the light at the precise wavelengths. Excited atoms do not absorb. They're already excited. They're already absorbed. So these calcium atoms, they need to be in the ground state. So the flame temperature is carefully chosen here to maximize the number of ground state atoms that are available. Now you have a cloud of free ground state atoms suspended in the flame. When the light from the hollow cathode lamp passes through this atomic vapor, atoms of the same element will selectively absorb their matching wavelengths. After passing through the flame and interacting with the free ground atom states, the remaining light continues into the optical system. The typical monochromator that they isolate the analytical wavelengths before finally reaching to the detector. So this is just how the optical part works. The detector then, of course, it measures how much of the lamp light was absorbed, and the drop in the intensity, because the intensity gets dropped due to the absorption by the sample, and it tells us the concentration of the element within the sample.